In this problem, we are given an ordinary differential equation and two initial conditions, and we want to solve the ordinary differential equation for the dependent variable x, or x of t, where our independent variable is time, or t. So if we look at the ODE that we're presented with, on the left-hand side we have an x double dot, and that's the highest derivative term we have of our dependent variable, so we can say that this is a second order ODE. And now on the right-hand side, we have a constant 3. It's not 0 on the right-hand side. This is a non-homogeneous equation. So when we go about solving this, we're going to have a homogeneous solution and a particular solution. And then when we add them together, we're going to get a total solution. Now we're going to solve this using Laplace transform. So the homogeneous and the particular are going to be solved for at the same time. And the two initial conditions we're given are also going to be incorporated simultaneously. And that's going to be the utility of using a Laplace transform to solve this for x of t. And looking at this again, we have a second order differential equation. So we're going to need two initial conditions, which were given: the initial condition on x of 0 and of x dot of 0, which usually we'll be calling the position for x, the velocity for x dot, if it's a mechanical problem. So to solve this using Laplace transforms, I first want to take the Laplace transform of both sides. So I want the Laplace transform of the left, and that's equal to the Laplace transform of the right. All right, so I need to go through and go from the time domain that I'm currently in into the frequency, the Laplace frequency domain S, by actually carrying through these Laplace transforms. So we want to look at our Laplace transform table so that we're going to be able to kind of algebraically manipulate these a little bit so that we know how to go from the time domain into the frequency domain. So I pasted in the relevant portions of the Laplace transform table with these listed here. If we look at our left-hand side to start, that's going to look like 12b. We have a second derivative of a dependent variable of time. So here it's f double dot and we have x double dot, but they're both just dependent variables of time. So I'm going to explicitly show some of the steps I'm taking here. I can take that 2 outside and I'll be left with the Laplace transform of x double dot. And I can take the 2 outside because it's a constant, it's not a function of time, so it's not going to be affected by this Laplace transform. And looking at the right-hand side, again, I'm going from the left side of my column to the right side. I'm going from the time domain to the frequency domain. The right-hand side looks like 1, which is a 1. And we can do that by, again, I'll show these steps in between. I can take a 3 outside, and I'll be left with 3 times the Laplace transform of 1, just to show exactly what I'm doing here. Now we can start to go through and actually do these Laplace transforms. So on the left-hand side, I'm going to carry through the Laplace transform of x double dot, so that 12b going from left to right. So that's going to be an s squared. And again, I'll put the line through the s so it's clearly an s and not a 5. So s squared times, on the table, it's f of s, but here little x goes to big X, minus s times x of 0, little x of 0, minus x dot of 0. So this is where the initial conditions are going to be included. And once again, that's an s there. Okay, so that's the whole left-hand side. I want to pay attention here. The 2 is multiplying all of these terms. They're inside the parentheses. So this whole stuff inside the parentheses, this is the Laplace transform of x double dot. And then the 2 just came along. And then on the right-hand side, I have 3 times the Laplace transform of 1. So looking at 1 on our table, going from left to right, that 1 is going to become 1 over s. All right, so I've carried through, I've done the Laplace transforms. I'm now in the frequency domain. So my next goal is I want to isolate any big X terms or X of S terms by itself. And I actually have only one of them. And actually along the way, I'm going to replace my initial conditions. So x of 0 is 1, x dot of 0, that initial velocity is -2. So I'll rewrite this while I'm here. So s squared big X minus s times 1 is just s, minus minus 2 is plus 2, equals 3 over s. Right, so again, what am I trying to do? Get big X by itself. I'll divide through by the 2 first. The order I do this in doesn't particularly matter because right now it's just kind of an algebra problem I'm working on. So I'll divide through by the 2, get that on the other side. And now I need that squared and squared still. Now I'm going to get as much as I can big X by itself, so I'm going to add an s to both sides. And I'll subtract a 2 from both sides. So I've moved the negative x from left to right and the positive 2 from left to right as well. And again, that as squared, I keep forgetting that. All right, so last step is I want big X by itself. Now, if we look at the right-hand side, right now I have it as 3 terms. And once I divide through by the s squared, we can see what it looks like and where we want to go from there. But I could combine all 3 of these terms over the 2s, but it's going to turn out that I'm just going to have to kind of undo that in a minute anyway. So I'm going to leave it as it is. I'm going to divide through by this s squared. So my first term, I have an s cubed in the denominator now, plus s divided by s squared is going to be a 1 over s minus a 2 over s squared. All right, so at least I have x by itself on the left-hand side now. So I will want to take an inverse Laplace transform of both sides. So I'll be able to go from big X to x of t, and then I have my solution there. But again, I need to pay attention to my right-hand side. Is it in a form yet, or can I manipulate it into a form that's going to appear on the Laplace transform table? And actually going up to here, I'll make a copy of this. We can see that each of these terms is going to look roughly like something in 3a or in 3b, really. So we have an s raised to a power in the denominator, and then we'll have a constant in the numerator. So it's going to turn out here, I don't want to combine them. I'm going to treat them individually because each one looks like 3b. And now when I do the inverse Laplace, I'll go from the right to the left. All right, so next step, let's do the inverse Laplace of both sides. So the inverse Laplace of this 3 over 2s cubed plus 1 over s minus 2 over s squared. So what we want to do to the right-hand side algebraically, again, is really going to depend what it looks like. Can we get it to look like something on our table? So at the moment, the inverse Laplace of this sum of 3 terms, that's not on the Laplace transform table, but the inverse Laplace transform of a sum is equal to the sum of the inverse Laplace transforms. So I can actually split this into 3 inverse Laplace transforms, each one of which does appear on the table. And I'll factor that negative out. 2 over s cubed. And the left-hand side, inverse Laplace transform of big X takes us to x of t. So once we go through and actually do these inverse Laplace transforms, then we're going to be set for what we need. Right, now I'm going to manipulate these as necessary so that I will be able to use my table to conduct my inverse Laplace transform. If I look at the first term, it kind of looks like 3b at the moment, but I'm going to rewrite it so that it looks exactly like what we have in 3b. All right, so the 3 over 2 I'm going to take to the outside, so I'm going to have in my denominator here, s cubed, I'm going to rewrite that as s to the 2 plus 1 power, just so it looks just like what we have in 3b. I haven't changed anything, that's still s cubed. But now if we look at 3b, our denominator is in the form of s to the n plus 1 power, where for the first term n is 2, which means I'm going to need 2 factorial, which is just 2 on the top. Now, I have to be careful though. I just kind of multiplied by that 2 factorial, which again is just 2, but so that I'm not changing anything about this, if I multiply by 2 on the top, I also need to multiply by 2 on the bottom, which I'm going to put on the outside of that Laplace transform. All right, so what did I do? I multiplied this by 2 over 2 so that the inside of the Laplace transform looks like something on the table, and then that 2 in the denominator I just have on the outside. So now if I look at this stuff here, it's in the form of this n factorial, I'll just write in general, n factorial over s to the n plus 1 power for n equals 2. So I will be able to now do the inverse Laplace transform because it looks like what we have on the table. That's plus L to the negative 1, or inverse Laplace transform of 1 over s. That actually is just 1 on the table as I go from right to left, so there's nothing to change about that one. Minus, I'll take the 2 on the outside here, and in the denominator I have an s squared, which I can write as s to the 1 plus 1 power. So again, it looks like 3b. I just have to make sure that I manipulate it so that it is going to look just like what we have on the right-hand side. So if it's s to the 1 plus 1 power, n is 1, so on the top I need 1 factorial. Well, 1 factorial is just 1. So actually in this case, I pulled the 2 to the outside, I multiplied the top by 1, so I already haven't changed anything about it. So now each of these 3 transforms is algebraically manipulated and looks like something on the table. So now I can finally do the inverse Laplace transforms. So on the outside here, I have 3 over 4, and then the inverse Laplace transform as I go right to left on 3b is going to take me to t to the n power, in this case 2. So 3/4 t squared. Plus, now on the table 1, going from right to left, 1 over s just becomes 1. Minus 2 times, looking at 3b, going from the right to the left, I'm going of t to the n power. In this case, n is 1, so it's simply t. So x of t, I am going to just rewrite this a little bit. I'm going to put it in ascending powers. So I'll just rewrite this as 1 minus 2t plus 3/4 t squared. And that is my complete closed form solution for x of t given the ordinary differential equation and the 2 initial conditions. And we can just do a quick check on our initial conditions, make sure that this solution satisfies both of them. So x of 0 is 1, x dot of 0 is negative 2. So let's evaluate x of 0, make sure that it matches. So if I put 0 in for t, I'm going to get 1 minus 0 plus 0 is 1. So again, x of 0, 1, x of 0, 1, that's my first boundary condition, or my first initial condition. So that's good. Let's look at x dot of t. So differentiating this, the first term 1 goes to 0. I have minus 2 plus, now I'm going to get here a 3 over 2 times t when I differentiate with respect to time. Now let's check that against our second initial condition on x dot. So putting in 0, I get a negative 2, and then the second term goes away. Negative 2, just double checking, negative 2 was the initial condition on the velocity, or on the x dot term. So this solution satisfies both of our initial conditions, and we've found what we needed to find. We found the value of x of t.